Okay, hello. Thank you, Suresh. Thank you, Professor Paik, for organizing. So the emphasis of what I want to talk about is the intersection with humans and water resources. And Yu Fong and Katie McCurley are two students that work in our group. And so the other thing I want to emphasize is I'm trying to promote what they're doing and what they're interested in, and I'm trying to encourage you to be interested in these things as well. So over the next couple of weeks, while they're here and I'm not here, I'd like you to want to talk to them more about these things that I'm going to talk about today, although I'll be here for the next 5 days as well. You can think of this as the summary slide of what are the main points, and I call this transferable themes because I feel like these are important themes for the questions we're interested in. But I think that these are also important themes for probably the questions that many of us are interested in different types of applications. As both Gavin and Professor Paik just talked about, in different types of networks we see strong heterogeneity, maybe different words to say that, and we'll come back to our words to say that. And the heterogeneity that you often see is in the structure of the network. I'll call that the topological heterogeneity. And that heterogeneity is in the types of networks that we're interested in, and maybe many of you are interested in. That type of heterogeneity is overlain on landscape heterogeneity, physical heterogeneity in space, where there's different types of landscape properties that would be heterogeneous, different types that might be of interest to different problems. And then very critical for what Professor Paik just described and for what we're doing and what we're all doing, it's not just the structure of the network, but the function, and many times the function we're interested in is some type of flow through the network. And then transcending that type of question and analysis is to think about interconnected networks. And again, it's the same for us when we think about the distribution of people on the landscape and how they interact with water. So we're interested in where the people are, and cities is one way to say that. It's not the only way, but it's a common way, and there's a rich history of thinking about cities. So those are somewhat interchangeable concepts. And I'll first start talking about the structure of the heterogeneity of where the people are. So we know that people live in different places, and we know that people live in different size settlements or cities of different sizes, right? We're in one of the biggest cities in the world right now, and many people live in smaller cities. So why do people sort themselves the way they do, and how is it that they're sorted? And so here you see a classical size distribution. It's called a rank size plot of cities, and this shows the ubiquitous power law type behavior. And Professor Paik reminded us of Horton's laws from the 1940s, and George Zip first claimed to be the first one to talk about this in the 1940s as well. So it's long been observed that we see so-called power laws of city sizes. And what that means is you have a small number of very large cities and then a large number of smaller cities. But another way to say that when you see these power laws is to think that it's a fat-tailed distribution, is that we have a wide range of sizes of cities. And again, there's a long history of more than 100 years of people asking questions about why this is. And so there's different explanations that have been offered with differing degrees of success. And so just to quickly review some of that history of that literature is the sort of geographer explanation. And the classical concept there that I think everybody should have some familiarity with is the central place theory. And we could think of, if you start over here on this side, and you can think of agricultural producers, and they go to the market to sell their goods, and then they also need to buy supplies for the farm, and so you would go into the market town. And so then every region would have maybe a market town. But then different types of products that you would want to buy, the region, the space of the number of consumers that it would take to support that industry might be different for farm implements versus piano manufacturers. And so there'd be different sizes to support those different types of industries, and then there'd be different transport costs. And it's the tension between those that leads to a distribution of sizes. Again, this was back to the 1930s. It was formalized, but the discussion about it even predates that. Similarly, there's an economics viewpoint, which is different, but it's got a lot of overall similarities. And here we could think about economic activities, and this is a nice economics plot of the utility of individuals, urban residents. And if we think about the size of a city and the utility for people who live in the city grows as the city grows, but then if the city gets too big, then the utility decreases. And the notion is there's different types of economic activities, and for a textile manufacturing location, you maybe only need 15,000 people for that to be functional, but for banking industries, maybe you could support more and more people. And the tension here is between the congestion costs of, as the city gets bigger, then you pay for traffic congestion and you pay a price for the land rents getting higher. And so that leads to a sorting of different activities in different places, and these different optimal sizes of cities for different activities leads to a distribution of sizes. Where again we pause and we say, what the discussion, the historical discussion, is trying to explain why these different sizes of cities. Why do we have cities of 20 million people and cities of 100,000 people? We can call this framework different things, but it's popular now to call it the economic geography perspective. And I called it that here because we just talked about the geography and the economics, and so this is the economic geography. And so if you say, if there's a new economic activity, or if a new group of people move to a place, if you have some immigrants, where are they going to move to? And if we said that the probability of the people moving to a certain place is proportional to the population that's already in that place. This is called Jawitz's law from economics, or we would call it law of proportionate effect, or a first order process, or multiplicative process. In any such process, this leads to you might recognize that as the genesis of a log normal distribution, or looks a lot like a power law. It's a fat-tailed distribution. And so if we accept this postulate, then that leads to these observed types of relationships. And the Nobel Prize-winning economist, Paul Krugman, he wrote and commented on these questions himself. And he said, look, this is a very simple model. It doesn't, he said, nihilistic, meaning it doesn't tell us much about the microeconomics of the systems. It's very simplistic, and we shouldn't really take such a model very seriously, except for one thing. It seems to actually predict the observations. So between the central place and the economic perspectives, we're able to get some insights into why we have different city sizes. And there's a whole history of literature of people trying to match those power law plots of the rank size. And they do a pretty good job of matching those rank size rules. But what they don't tell us about is, where should the big city be? If I was to make a prediction, where in the landscape is the 20 million person city, and where are the 100 million people cities? It just tells us how many of those we should expect. So that brings us into starting to think about the intersection of where the humans are and the heterogeneity of the landscapes. And again, these are questions that have a long history. So I've given you a quote from the Milanese from Italy, the post-Machiavellian political philosopher thinking about cities, Giovanni Botero, and he said that the greatness of cities can be explained by factors that feel very modern to us to talk about. Oh, it's about the soil suitability, the location of the site in terms of its transport route access, government policies, etc. So again, a rich history of thinking about the connection of where the people are and what are the landscape heterogeneity factors. So what factors, for example, could be important? So here is a relatively little-known data set from the global population and the elevation. So if I look at all the people around the world and what elevation do they live at, we already know many people live close to the ocean, and so therefore relatively close to sea level. And so we'd expect that as you get to very high elevation, not many people live there. It's not very well known, I think, about how there's such a large peak at this what to me feels like a pretty high elevation. And there's a few different potential explanations for that. For example, the rich volcanic soils at higher elevation in certain latitudes, or maybe getting away from malarial type diseases at low elevation. But the general principle is that the location of where the people are and landscape features starts to become evidently apparent. So there's elevation. Now we can think about the slope of the landscape, and this gets us a bit closer to hydrology. This is a paper from analysis of where the people live in Japan in relation to the topography and then the river characteristics. You see over here we have the Horton bifurcation ratio, and over here we have the stream order, and we have here the population. These are log plots of where do the people live in relation to landscape hydrogeomorphic characteristics, and we see a very strong relationship. And it tells us that people live close to the big rivers. Okay, well that's good, and they don't live close to the small rivers. Or another way to say that is people live in the flatter lands and not so much in the steeper lands, the higher elevation lands. And so as these authors say, these very strong relationship was found in Japan, and so it's maybe that's because it's a long history of a unified governance and management structure, or maybe it's because of a relatively homogeneous, and I would say, or maybe this is a steady state that's been evolved to, and so these data and the other types of analyses so far have been static analyses, and so one of the things that we would suggest and are interested in promoting is to try to look at a dynamic evolution analysis as well. Similar static from literature, a static analysis of where the people live with relationship to landscape features of interest of where the water is. And if you went to Yufeng's poster or saw her presentation yesterday, she mentioned this study by Kumu et al. And this is, again, from a global analysis of where the people live and the relative aridity, and we can see that that there's a higher percentage of people that live close to water in temperate regions as compared to arid regions. And so you might have expected in arid regions people would live close to water. And so that might have first seemed counterintuitive, but if you normalize and remember that in arid regions, the distance between water sources is much higher. So if you normalize where the people are compared to the distances between water sources, which is what this ratio is here, we see that in, for example, temperate North America, that's a ratio unity, which is analogous to people live kind of homogeneously around the landscape if there's water everywhere, which is kind of what we might expect. And we see that in arid regions in North America, people live a bit closer to water. But it's instructive to compare that to overall, this is all of East Asia, and you see that in East Asia, even in the temperate regions, people live preferentially closer to water, and in arid regions, even more preferentially closer to water. So this is kind of interesting to think about in terms of maybe economic development stage and technological evolution, and how that's maybe altered a relatively natural to a more hydraulically manipulated. But again, this is a static analysis. We're interested in trying to evolve through these technological stages. We got 2 weeks to do it. Another static, and this is our group's work, but another static analysis, again, was the humans and water. We looked at all the cities in the United States, and we looked at the how do those cities get their water. And so we looked at all the surface water availability, all the water storage, all the groundwater, and these open circles here, this is the amount of water that's available, liters per capita per day, and this vertical solid line is a measure of enough water. We can debate what's the right number, but it's the demand that is the average of U.S. cities. And these open diamonds are the naturally available water. And we can see that we've got many cities, Las Vegas, Phoenix, Dallas, Fort Worth, Denver, Los Angeles, many cities in the United States where the people live in a place where there's not enough. Well, this is not a big insight to say people that live in the desert is a place with not a lot of water, but we quantify the total number of people in what cities, and we say there's not enough water. But then if we use what I call the hydraulic-based method, and we say that the people in the cities have economic power, political power, so they capture water from other places. And if we analyze where they actually get their water from, we see that now all the cities in the United States have enough water. So this is again another way to see of the human interaction of cities and water, and we conclude from this that cities, people are likely to get enough water, and we see this evolution, this dynamics. There's embedded in here a dynamics of people getting water, but for this case, this was just a static analysis. We're interested in going to a more dynamic approach, which brings me to what Yufeng talked about yesterday and what her poster is about, and again, what she'd like to talk to people more about over the coming weeks is a dynamic evolution of where the people are, and a dynamic evolution of how they access and interrelate with water. And embedded, I don't have a slide to tell you more, is embedded in that is technological evolution as well. So what she's starting with is this is the human population from census data. So this is the sort of European migrant human population in the eastern United States origins, and then evolving all the way to cover the whole United States. And in the early phases, there's hypothesis, a very strong connection of where the water resources are, and in the modern phase, as indicated by what I described with that Kumu paper, there's a bit of a disconnection as technology allows us to separate. Okay, but how do the networks enter into this? I've so far just talked about humans and water more abstractly. Once again, a rich history of thinking of humans and cities even, and human settlements as networks, and as nested networks. If you talk, as I just have, as a city as a macro system, if I draw a box around a city, then I'm thinking about a collection of people, and there's a fallacy to think of that as one actor making a decision. Instead, we go to micro scale, and we look at actors within the city making decisions, and we can look at all the different types of networks, and many of us are doing that. And then I would also suggest that it's very interesting to go to a more macro scale and think about the networks of cities. And so this study in the United States of all the cities and where they are in relation to the water, I think that's a direction that we want to go. So many of us who are looking here at the micro scale within a city, and some of us are looking at individual city, and what we're trying to do is look at this interconnections of many cities. So let's talk about the structure of the networks and the flows of networks in this sort of human cities water perspective. Zachary Neal has done a few studies of looking at networks of cities and flows between those cities. So in this particular example, it's internet connectivity, the backbone of the internet, and this is in cities in I think it's a collection of 90 cities around the world, a data set of the internet connections, and there's measures of centrality and measures of power, and this little example here kind of illustrates that this city in this location has a central location, but it's not as powerful, and what that means is that it doesn't totally regulate the flows of the cities on the connecting nodes, whereas here, this city and this city, or these nodes, in order to transfer, to have flows between those, they have to go through this central one. And then the power and the centrality, we can see that you could have a low degree of centrality and a high degree of power, and he would call that a gateway city. You can have a high degree of centrality and a low degree of power, and you would call that a hub city. Or you could have high centrality and high power, and those would be what you call a very important global city. So it's a notion of taking a structural measure and a flow measure and relating them and thinking about them together. And this is not necessarily a novel thing to do with a network. This is what people will do with all kinds of networks. We've done it ourselves with social networks. And I just wanted to mention real quick that work because it's important to think about. This type of metric is a whole network metric, as differentiated from what we would call an egocentric network analysis. Although the structural measures that you hear about, centrality between this, are not that different. And so an egocentric network instead of the whole network is if you take one node's connection to everybody that that node is connected to, rather than thinking about everyone's connections to everyone. And sometimes it's much easier to get data on an egocentric perspective. For example, we worked on a subject that's, I think, of important to many of us scientists, is citations and H-indexes. So I just put here the snapshot of my Google Scholar page and to sort of get us in the mindset of thinking about H-indexes. And so we wrote this paper. We did this study where we asked questions about the structural characteristic of authors' egocentric collaboration network and the flows through that network and the impact, the property that comes out of that we might be interested in. What property might we be interested in? Well, the citation impact, the H-index. And so we tested a whole bunch of fancy structural measures, and in this case we found that size is all that matters, the number of collaborators that you work with. But take-home point from this, we did egocentric measures rather than requiring a whole network, and those are other ways to think about the structure and the flows. The structure of the network is usually talked about, as I just did, in terms of the topology of the network and the interconnectivity of the nodes. And I'm now turning the corner to start to think about, I started by talking about central place theory. And so it's really, I think, important to have a comfort level with both of those when we talk about landscape heterogeneity, people, where they live, and to think about both the topology of the network and the topography and the actual embedded in space. So again, Zachary Neal looked at the, basically what these numbers here on the y-axis are some measure of the, in a correlation, multilinear regression, and the strength of the impact of the size hierarchy of how big the city is on determining the importance in the global economy, and on a decadal scale, and then the network connectivity. And so the hypothesis, and these data arguably would support it, is that this evolution in technology and an evolution in the importance of being globally connected network city has led to a decrease in the importance of being a big city and an increase in the importance of being big city, meaning that the hierarchy of the size is what controls things, versus the hierarchy in terms of your position in the topology of the network. Which brings me to thinking, I mentioned Yufeng's work, and so what Katie is interested in is also about the structure of the topology of the network and the flows through the network. And maybe you recognize this diagram, which she showed up here yesterday and on her poster as well, which is a measure of flows of trade through a network of South American countries. And I talked about how there's a economy and society history of thinking about cities and networks and flows between them. And what we would propose and think is very interesting is to have a bit more broader systems perspective of this and integrate the economic, societal decisions and ecological, hydroecological, eco-hydrological perspectives as well into a more comprehensive model. Okay, my point that I was leading us up to now is to think about this notion of the networks embedded in space. And when it comes to analyzing networks in the past 15 years, the physicists have really taken over. It used to be that networks were the domain of, I'd say, social scientists and maybe a few river networks people, and the physicists have really gotten in there and done a lot, and so they're the ones who are publishing in Science and Nature mostly. And they would take all kinds of macroscopic data sets. For example, this is the air travel network and inter-county commuting. And what I'm highlighting here, if we look on the right, these are the topology characteristics of the node degree distributions. And we see that these two distributions, or these two networks, have, I'll just say, qualitatively similar node degree distributions, which you might say is kind of a power law-ish shape, and whether they have the same slope or not. The main thing is you can say, oh look, those node degree distributions have some consistency with our expectations. But if I look at the length distributions of the connectivity of the distances that one has to travel to go from one node to another, we can see quite a big difference between these. And so just looking at the topology alone, without thinking about how the network is embedded in space, doesn't give us the full picture. Here's a couple more examples on that, right? So this is from nature physics. And what we see is, again, a similar thing. This is the airline passenger loads, the flows of passengers between hubs in the United States. And we see this sort of network from real data and then network from a model where very simple model where it's critically based on not on this is the classic power law structure of the degree distribution where this alpha parameter would be the parameter similar to what Professor Paik was telling us about, where it's the node degree distribution. And so these authors introduce a slightly different, but not hugely different concept to thinking about what they call the network dimension, where it's the node degree and the spatial dimensions embedded together. And we get, again, a very similar relationship. But if we think about this network dimension and we run a quick model, we can arguably see some qualitative similarities in those overall structures. And then they have some other papers which show that the other, not just the structure, but the functions we're interested in. The percolation, which is about the vulnerability, or the diffusion of the flows of information and flows of people, the flows of goods through the network can be well described if we think about the topology plus the spatial embedded characteristics. How do we describe the spatial interactions between nodes? Again, here is some data from the US Census of commuting distances. I was fairly shocked when I saw this, that people in the northeastern US, there's not a lot of people. These are the fat tail. There's some people who would commute very long distances. Most people commute short distances. And if I want to, okay, I'm willing to accept that we should do spatially embedded. We should think about the actual distances of the topology of the node connections. How far does one have to travel? And I'll use a gravity model, which is the common way to use the attractiveness between nodes and distance. And if I use a gravity model, I would get something like this. And the node degree distributions with my spatial model is very similar to the real data, and so success. But you can see that I've totally failed to capture those long distances. And so they introduce again, not very complicated, but a different spatial model, a radiation model, and they're able to capture the node degree distribution very well, and a much better representation of the commuting distances and the actual distance. So again, summary is the topology plus the spatial characteristics of where things are, I think is a good direction for us to go in. So I've said spatially embedded. I've said a little bit about dynamic, and then the next and final thing is the interconnected networks. And this is not that different from what I was talking about with the work Julie Podowski and a student and I had done with the cities in the United States, where we looked at cities and how they get their water. And this is some work by Rachamuni Pikaral when he was at Arizona State. And this is a paper that I wished I had written. Here you can see cities and resources. It's very generalized, but I would think of it as like an aquifer or a river and getting their water or whatever the resource is that supports the city. And what they did is a network of cities and a network of resources. And how would I do the competition? Well, they just did a Lotka-Volterra, right? A predator-prey type of model. And you can see some relatively simple governing equations, and they put together a model of sort of general principles, and you can see in the end it leads to conclusions which would be not that different from what one might expect. But it's some very elegant work, right, that right as the resources get depleted, some cities succeed, some fail, some peter away, some utterly collapse, some resources are able to be sustained, some are not able to be sustained. But it's and you can see this paper is just from a few months ago. It gives us some hope of some directions to go if I want to do interconnected cities and interconnected resources, and I want to have a modeling framework where I can have not just interconnected cities and not just spatially embedded, but also the dynamic evolution of the relationship between consumption and production of resources. I'd like to quote somebody else who's saying the same things that I'm saying in a paper, a review from networks to networks of networks from 2014. And these authors concluded, right, that further studies, we should focus on analysis of real data, which I think is one of the themes of what we want to do in the next couple of weeks. We should think about real data. We should think about real networks embedded in space. We should think about the interdependency of networks and how the vulnerability of those interdependent networks might be affected by the network structures. On this notion of interdependence, maybe some of you have seen these papers in Nature Science and various nature subsidiaries where the physicists do things like, the physicists will do things like look at examples of different types of interconnected networks. Here's a lattice, here's a random network, here are two lattices, a random network and a lattice, two random networks, a random network, and a spatially embedded network. So this is the actual power grid for Western Europe. And then they'll do things like vulnerability analysis. Maybe you've seen these types of plots where this is, if I remove some fraction of the nodes randomly out of the network, then what fraction of the rest of the network stays interconnected? And if I remove a small number of nodes and the connectivity of the network then collapses down to a small number, we would call this a very vulnerable network, and this would be a more robust type of network. And so you would look at this and conclude that, oh, this is bad and this is good, and they say, well, these are the interconnected networks, and thus, what do they say, right? Extreme vulnerability of interdependent networks. But a key thing to remember is these are physicists and they just did random interconnected networks. So once you get a little bit more detailed, and so here's an example where they looked at the spatially embedded networks where they're not totally random, but they're actually correlated. And so this is the global airport and global seaport coupled networks, and you can see randomly interconnected networks, and you can see that this is the fact that major seaports and major airports are not random, but are more spatially correlated, and this is less vulnerable interconnected network. Again, I think these are interesting, important directions and concepts that we could carry with us forward. And the very last idea that I throw out there that we should think about, what about the functions? There's many different types of functions. I said flows through the network. Quite an exciting perspective on networks that Louis Bentoncourt and other collaborators at the Santa Fe Institute published in Science and Proceedings of the National Academy of Sciences is thinking about network scaling laws. And here you see the population of cities. This is talking about cities. Population of cities, and then some service or some activity in the city. And so this solid line here is a one-to-one line, or you could say it's a slope of 1 on this log-log plot. So it's a linear behavior. And so for this example, which is the road miles traveled, we see what they call sublinear behavior, or this exponent of less than 1. And many different types of processes across many different types of cities they found would be less than 1 or equal to 1 or greater than 1. And the creative things like patents and other innovation metrics tend to be super linear. And so what does this mean is that big cities are places which are more innovative. Again, people have discussed that for a long time, but a data and a theoretical framework, empirical data and theory to support that are relatively new. One reason I want to conclude with this is because we have, many of us, maybe again what I said earlier, is that within one city we have different types of networks that are very detailed, and Suresh, for example, is looking at the topology of those networks, and what do we expect in terms of this sort of, okay, we know it's going to be a power law, but what will be the slope of that power law? And I would suggest that this wave of innovation and this change, this dynamics over time is an important framework for us to reflect on that, because if it's a common technology that every city should have, like we think in the developed world we should all have water supply systems and wastewater collection systems and road transport networks, then that would have an exponent close to 1. And if it's a leading technology, right, that would start at the big cities and trickle down through this hierarchy that I introduced this talk with. And if it's an older technology that's maybe fading out, then the biggest cities have moved on beyond that, and you would see it preferentially in the smaller places. And that's where we'd expect the sublinear behavior. So we have, I guess, some empirical linkages to tie us to this evolution over time. So right, in conclusion, what I think are important ideas for us to reflect on are the hierarchy of cities, which we know are highly heterogeneous. We have geographical and economic and even hydrogeographic explanations to think about why the people live where they do. We can think about the flows through cities, flows of people, flows of goods, flows of information between cities on networks. And we can think that those cities are embedded in spatially heterogeneous places with heterogeneous properties, and we have some potential tools to actually analyze those. And we can even think about the vulnerability of those interlinked networks and then the services they provide. Thanks very much.